In this video, we explore the concepts of true vector and relative vector, essential for understanding ship movement on radar and electronic navigation systems. True motion shows your ship moving on the screen according to its real course and speed, with land and target staying in their true positions. A 6-minute true vector displays where each target will be in 6 minutes if its course and speed remain unchanged. In contrast, relative motion keeps your ship fixed at the center of the radar. All other targets move relative to your ship, making this view useful for collision risk assessment. A true vector shows the actual movement of a target over the ground, reflecting its true course and speed. A relative vector indicates how the target moves in relation to your own ship's movement, which helps assess collision risk. In summary, true vectors show movement over ground, while relative vectors show movement relative to your vessel. Let's compare true motion and relative motion to see how each method affects the way targets and your ship appear on the radar display. True motion displays your ship moving on the radar according to its real course and speed over the Earth. Land, buoys, and other ships appear in their true geographic positions, making it easier to understand actual traffic movement. On a true motion display, your ship moves based on its actual course and speed, while land and fixed objects remain stationary. In relative motion, your ship stays at the center, and all targets move relative to you. A target moving directly toward the center in relative motion suggests a collision risk. Now let's look at the concepts of ground-stabilized and sea-stabilized radar displays, which affect how true vectors are presented. In ground-stabilized mode, the radar uses GPS course and speed over ground. Targets' true vectors reflect their movement over the ground, including the effects of current and wind, giving a real-world picture of vessel motion. In sea-stabilized mode, the radar uses gyro course and speed through water. Here, true vectors show movement through the water, ignoring tidal current and wind, and display course and speed through water, not over ground. Ground-stabilized mode uses GPS data, reflecting movement over Earth's surface and including current and wind effects, ideal for navigation. Sea-stabilized mode uses speed through water, ignoring current and wind, best for collision avoidance and ship handling. In short, ground-stabilized equals over ground with current, and sea-stabilized equals through water without current. Ground-stabilized true vectors assist with navigation, showing your ship's actual track over the ground and helping with route planning and coastal navigation. Sea-stabilized true vectors are used for collision avoidance, showing vectors through the water, making it easier to judge risk and closest point of approach. Relative motion displays are favored by mariners for identifying collision risks. Sea-stabilized true vectors are used for collision avoidance, while ground-stabilized true vectors assist with navigation. Here's a comparison. Sea-stabilized uses the ship or sea as a reference, doesn't require GPS, gives relative bearings, and is best for collision avoidance. Ground-stabilized uses Earth as a reference, requires GPS, gives true bearings, and is best for navigation and mapping. ECDIS, or Electronic Chart Display and Information System, is a navigation information system with backup arrangements, accepted under SOLAS regulations. It displays information from the system electronic navigational chart and integrates radar, AIS, and ARPA overlays for navigation. Next, we examine how ENCs, ECS, RCDIS, vector charts, and raster navigational charts relate to each other in electronic navigation systems. This table compares ENC, vector charts, RNC, RCDS, and ECS. NNs are official, vector-based charts used in ECDIS and are mandatory for paperless navigation. RNCs are raster charts used in RCDS mode and require paper chart backup. ECS is unofficial and cannot replace paper charts. Electronic chart systems use two main types of charts: raster navigational charts, which are digital scans of paper charts, and electronic navigational charts, which are vector-based. RNCs are less interactive, while ENCs support advanced features such as alarms and data layers. NIs offer seamless coverage, remain clear when zooming, adjust orientation automatically, support safety alarms, and allow interrogation of chart objects for detailed information, enhancing safe and accurate navigation. Raster navigational charts lose clarity when zoomed in, cannot suppress unwanted layers, may have datum inconsistencies, and offer less flexibility compared to vector charts. Official electronic charts, both RNC and ENC, are issued only by authorized hydrographic offices and meet SOLAS carriage requirements. ENCs are converted to sync format for system use. INCs have usage bands such as overview, general, coastal, approaches, harbor, and berthing. The third digit of the ENC number indicates its usage band. For example, a 3 means coastal. Scaman controls the visibility of chart features, reducing clutter at small scales. Important objects may disappear if the scale is too small, so careful zoom management is important. CATSOC indicates the reliability of chart data, ranging from 6 stars for highest accuracy to 2 for low confidence. It affects position, depth accuracy, and seafloor coverage. ENC charts are updated through digital downloads via CD, email, or internet. Updates are sequential, and ECDIS logs the update history for compliance and safety. ECDIS allows users to add manual updates, such as symbols and notes, for passage planning. These changes are saved separately from official ENC updates. ECDIS does not meet IMO performance standards, while ECDIS meets SOLAS chart carriage requirements. RCDS mode is used only when official ENCs are unavailable, and paper charts may still be required as backup. According to SOLAS V, only charts issued by government-authorized hydrographic offices are official and can fulfill carriage requirements, provided they are kept up to date. SOLAS does not technically define ECDIS, but requires ships to carry adequate, appropriate, and up-to-date charts, whether paper or electronic. When using ECDIS, official ENCs must be used and regularly updated. When ECDIS is used to meet chart carriage requirements, it must use official ENCs issued by hydrographic offices. The navigator can select which information to display, with safety-critical features always available. ENCs are official electronic chart data. Inside ECDIS, they are processed into sync format for navigation. ECDIS can replace paper charts only if it is IMO type approved, uses up-to-date ENCs, and has a backup arrangement. This table compares ECDIS, ECDIS, and RCDS. ECDIS is ECDIS is IMO approved, can fully replace paper charts, and uses vector charts with automatic safety features. ECDIS is not IMO approved and cannot replace paper charts, while RCDS can only replace paper charts when compliant with specific requirements. ECDIS performance standards are set by IMO A817-19 and its amendments, covering operation, display, updating, alarms, and backup arrangements. ECDIS enables rapid route creation and modification, supports automatic safety checks, and detects hazards based on safety parameters. Key safety parameters in ECDIS include the safety contour, safety depth, and safety frame or cone, which help ensure safe navigation. ECDIS accuracy depends on sensor inputs and can be affected by chart datum inconsistencies. Over-reliance on the display or improper scamming settings may hide critical information, so navigators must cross-check and remain vigilant. Maintain situational awareness by monitoring outside the bridge, using radar overlays, avoiding excessive menu navigation, and cross-checking GPS positions with independent methods. This presentation was created by Captain M. Ahmed.